All right, today will be our first lesson in Unit 14. We're going to be talking about radical expressions and equations in this unit. So we will start with simplifying radicals and talking about what those are. In Algebra 1, we're basically just going to be focused on working with square roots. So really kind of the focus here for the next couple of days is that we'll be able to simplify square roots with perfect square radicands. You guys will be able to simplify square roots that have variables as well. And today we'll be working on the ones with even exponents. On Friday is when we'll get to odd exponents. But basically we'll kind of work through this simplifying portion. You can take a look at the guide here and kind of see what it looks like here over the course of the next few days. Wednesday, Thursday, and Friday we'll be simplifying again on Monday. Tuesday and Wednesday will be your time to review and practice, and then Thursday we'll take our first assessment. So going down to the day one notes, you'll see your learning targets are at the top. We're going to go through some basic vocabulary to start, and then we will progress our way through kind of what the simplifying process looks like. So an expression such as the square root of 64, that is what we call a radical. The symbol is called, so the square root symbol is called a radical. So we have, I should add expression after this. The square root of 64 is what we call a radical expression. This symbol, what many refer to as the square root sign, is really called a radical. A square root is a specific case of how we use that, but it tells us to take the square root. We're working on perfect squares and square roots in this unit. So really, there's this little number, it's called an index, that goes outside of the radical. When this number is a 2, that implies that we are taking a square root. But when we work with square roots, they commonly don't put that 2 there. It's kind of like putting a 1 in front of a variable as a coefficient. You don't need it. We have cubed roots, fourth roots. Ideally, you could put any number you want there. We're going to take the fifth root. Those are radical expressions you'll focus on in Algebra 2. In this unit, we're really just focused on when we take a radical with an index of 2, which is simply wrote as just the square root. So we'll just be working with square roots in this unit. The number variable under the radical sign is what we call the radicand. So in this case, the radicand for the square root of 64 would be 64. Given the problem square root of 49, be sure to state the positive or non-negative answer. Okay, the calculator is what also gives you the square root. So the square of 9, that would be 9 squared, that's 81. The square root of 9 is 3. So when we talk about the square, that would be to the second power. When we talk about the square root, what number to the second power gives you that number. I'm going to have you guys fill out the square roots here for our perfect squares below. I'm going to go ahead and pause the video, then you'll press play and check your answers. All right, you can see the square roots that I have filled in for you. Square root of 1 is 1, square root of 4 is 2. I'm not going to go through all of those. You guys can fill in that table as needed. When we raise something to the power of 1/2, like you'll see this notation here, that's really the same thing as taking the square root of a number. So 4 to the power of 1/2, that's 2. 16 to the power of 1/2, that's 4. 25 to the power of 1/2 would be 5. The square root of 25 is equal to 25 to the power of 1/2. Those are the same thing, which is also equal to positive 5. So just different notation. This would be in a radical form. This would be exponential because we are raising it to a power. We're going to go through a couple of examples here, not use a calculator. Square root of 121, that would be 11. You'll see we have this plus or minus out in front. This would be similar to like when we were using the quadratic formula to solve quadratic equations. You're going to take the square root of 169 and then keep the plus or minus out in front. Here we have negative root 196, or negative time. This is really like a negative 1 times the square root of 196. So basically, you'll take that square root of 196, that's 14. That answer stays negative, so the negative stays out in front. If you see a radical underneath a radical, that means you're going to take the square root of the inside first. That would be 25. So the square root of 625 is 25. Then we can take the square root of 25. That's positive 5. You'll see sometimes we have fractions. You'll take the square root of the numerator and the square root of the denominator separately. Square root of 4 is 2. Square root of 89 is 1. So if you're taking the square root of a fraction, take the square root of both the numerator and the denominator. This next one's a little bit of an application problem here for you, or not really a problem, but just to get you thinking. What's the side of a square for an area of a square which is 9? Well, if the area is 9, what number times itself, because a square has 4 equal sides, is equal to 9, then we would know that the side length is equal to 3, because 3 times 3 would give you an area of 9 squared. All right, in this next example here, you'll see we're multiplying like radicand. So we're taking a radical and we're multiplying it either by itself or by the same number. So the square root of 7 times the square root of 7. If we follow this rule from up above, where a and b are both greater than or equal to 0, then the square root of a times b, and if a and b are equal, would just be a b, would be the same as square root of a times the square root of b. So you can pull those apart. But if you have two radicands, we multiply those together and keep them under the radical. If we are multiplying like radicands, square root of 7 times square root of 7, that's square root of 49. That's going to simplify to 7. Same case here, square root of 3 times the square root of 3, that's the square root of 9. We know that that is equal to 3. So if you multiply two radicals together and the radicands are the same, you're just going to be left with the radicand. So square root of 3 times square root of 3, that's square root of 9, but that simplifies to positive 3. So basically it gets rid of the radicals for us. So if we're multiplying two square roots or two radicals together, you multiply the radicals and then keep that square root. If we can simplify it, then we can. If not, we will leave it as just one product underneath. Now, I just mentioned simplifying, what that means. We want to be able to take a radical expression in the simplest form, where we don't have any perfect squares left underneath the radical. So we want to simplify it and kind of break it down the best way that we can. The easiest way to do this is going to be looking for perfect squares that go into the radicand. So if we have the square root of 150, we want to think about some numbers that multiply to 150. In this case, as long as we're thinking about using a perfect square, you can always simplify later if needed. But I know that 25 is a perfect square, and 25 times 6 is equal to 150. Now, if we use this rule from up above of multiplying two radicals together, then I can take a product and split it into taking the radical of both factors. So I can write the square root of 50 as the square root of 25 times the square root of 6. Now I look to see if I can simplify either of these. The square root of 25 simplifies to 5. I cannot take the square root of 6. So my final answer is 5 times the square root of 6. This would be the simplified form of the square root of 150. We pull apart that radicand in terms of a perfect square, take that square root, and that number goes outside of the radical. And then anything that we can't simplify is going to stay underneath the radical. So if we have the square root of 48 here, well, we want to think about numbers that multiply to 48, preferably ones that have a perfect square, which means you want to see, can we use numbers like 1, 4, 9, 16, 25, 36, 49. Those are all of my perfect squares. Those are the numbers I want to check first to see if they go into my radicand. So if we have the square root of 48, I know that 16 goes into 48 3 times. 16 is a perfect square. So I can rewrite the square root of 48 as the square root of 16 times the square root of 3. Because 16 times 3 is 48, we can split that product into two separate factors. The square root of 16 is 4. I can't take the square root of 3, so my answer stays 4 root 3. Coefficient goes out in front, then the number followed by the radical. All right, next example, we have 2 times the square root of 18. We have that coefficient of 2 out in front. So I'm going to write the 2. Then I'm going to take the square root of 18. Remember, we're looking for perfect squares. I can't take the square root of 18 alone, but I do know that 9 and 2 multiply to 18. Well, 9 happens to be a perfect square. So 2 times the square root of 9 times the square root of 2. Square root of 9 is 3. So 2 times 3 times the square root of 2. So it's kind of like breaking down each factor individually. Square root of 9 is 3. Well, these are both coefficients now. 2 times 3 is equal to 6, followed by the root 2 that stays out in front. I'm going to have you guys do 13 and 14 and then check your work. All right, so go ahead and check your work in examples 13 and 14. We're going to go ahead and talk about examples 15 and 16 here. You'll see that now we have a variable underneath the radical. If you remember from earlier, I talked about how if we're taking the square root, that means we have an index. It's typically not written, but it's a little 2 that goes with the radical that tells you the square root. Basically, it means you're looking for groups of 2. So we take our exponent, and we're going to divide it by 2. So we're going to divide it by the index. We'll see how many times it goes into it. If I ask you guys what the square root of a squared is, you would all tell me a. Well, that's a to the first power. 2 divided by 2 is 1. If we took the square root of x to the 6th, we'd be splitting that apart to x to the 3rd and x to the 3rd because we are adding the exponents. Well, what's 6 divided by 2? That would be an exponent of 3. So we split apart the number underneath the radical by finding perfect squares. We split apart the variable with the exponent by dividing that exponent with a 2. So we'll put it all together here in example 17. I like to split apart the radical right away. Rather than looking at the square root of 25 times a to the 4th times b to the 8th, I like to split it. You don't have to do it this way. I do think it helps you stay a little more organized. Now I can find the square root of each part of that product individually. The square root of 25 is 5. The square root of a to the 4th, 4 divided by 2 for that index is a squared. And then b to the 8th, the square root of b to the 8th would be 4, because b to the 4th times b to the 4th would be b to the power of 8. 8 divided by 2 is 4. Final answer, I don't need to put the multiplication signs. 5a squared b to the 4th. You guys will try example 18 on your own, and then I will show you the answer here in just a moment. In example 18, split apart that product into the separate terms. 36, x to the 4th, y squared, z to the 6th. Square root of 36 is 6. And then we're going to divide all of our exponents by 2. So 4 divided by 2 is 2, x squared. 2 divided by 2 is 1, y to the 1st. 6 divided by 2 is 3, z to the power of 3. I'm not going to do the next 3 examples with you. You guys can do those on your own. You'll notice that the notation is slightly different. Those are written exponentially. But remember, anything to the power of 1/2 tells you that you are going to take the square root of that quantity. So go ahead and rewrite it with a square root sign. I'm going to pause the video to show you guys the answers, and then you'll be able to move on to tonight's assignment, which is worksheet 1. Have a great day.